We return now to function analysis. This is part 2. I'm going to do question 1 of the assignment just like I did for function analysis part 1. And make sure you run these things that I have provided for you. So here's the definition of the function. Make sure you run that. So that is in there. And double check and make sure that we enter the function correctly. Notice that it has automatically changed this cube root to a 1/3 power. That's okay, that's the same. Now, domain issues will happen this week, potentially. Now, in this particular function, we don't have any domain issues with the function itself. The domain issues are going to show up in the derivative. In question number 2, oops, all real numbers. In question number 2, we'll have some domain issues. So you'll have to deal with that and see what happens with the vertical asymptotes. There's examples of that in the notes. All right, let's make sure we run our derivative. So that's in there. I call my derivative df, and I asked to solve for where the derivative is 0. Now, one of the reasons I show the derivative here is so that I can check where this is not defined. So remember, derivative undefined is also a critical point. So we have to worry about division by 0. So if x squared plus 2x plus 1 is equal to 0, then we get division by 0 right here. And there is one solution to that. X squared plus 2x plus 1 is equal to x plus 1 squared. So x equals -1, it would give us division by 0 here. And so we have one place where the derivative is not defined. Maybe I'll write myself a little note here. F prime is undefined, or DNE, at x equals -1. Now, if you look down here, you should be a little disturbed by that statement, because down here it says derivative is equal to 0 when x equals -1. Does that make any sense? Well, let's ask it. What is the derivative at -1? And it says error, division by 0. So it recognizes that -1 is not a solution here, but it still gives me that as an answer. And so that's a little troubling. This means that whoever programmed the solve command in CoCalc didn't do it all the way. This is an extraneous solution. You may remember from pre-calculus talking about such things. The way that you would go about solving this equation, set it equal to 0 and try to solve for x, the solution technique would eliminate this problem at -1, and so this ends up being an extraneous solution. And CoCalc really ought to have been programmed to check and test that and see, and they didn't. So it's not a fatal error this time, because x equals -1 is important to us because the derivative doesn't exist there. So if you forget that, it almost is helpful, but in other situations that would definitely not be helpful. So be cautious. The solve command might give you some extraneous solutions inadvertently. At any rate, like I said in the part 1 video, I'm going to keep track of these critical points. So I'm going to write down that f prime is equal to 0 when x equals or f prime does not exist, rather, when x equals -1, and f prime is 0 when x equals -5/3. Now that one actually is correct. If you try df of -5/3, it should give us 0. Yeah, okay. So that one does work. Now let's not delete that. Okay. So those are my 2 critical points. I need to see if the sign of the derivative actually changes there. So let's start with the -5/3. So I need to take the derivative and put in something to the left of -5/3. Now, -5/3 is -1 and 2/3, so -1.6 repeating. So something like -2 would be to the left of that. Now be careful to the right of that. If you want to stick with whole numbers, you choose -1. We cannot choose -1. That's our other critical point, where the derivative doesn't exist there. We have to choose something that's further away. How about -1.5? And you can see here it gives us the exact value. And like I said in the last video, you can trick it into giving a decimal simply by putting a decimal point on the input. Did the sign change? Yes. So we have a local min and max in the original function. Which one is it? Well, look at the direction of the change. This is the first derivative test. The direction changes from positive to negative. In the derivative, that means the original function f changes from increasing to decreasing. So the picture is this kind of picture. It's a peak kind of picture. Up changes to down. So this is a local max at x equals minus 5/3. Oops, forgot the minus sign. And I'm going to write that down here on my little scratch paper. I found a local max. When I go and graph it in a later step, I want to make sure that that shows up. And now we're at, oops, not that yet. We're not done with this step. We still got to do -1. So something to the left of -1. Now don't go too far to the left. You know, we can use the minus 1.5. That's fine. Just make sure you don't pass the minus 5/3. To the right, we can really choose whatever we want there. Did the sign change? Yes, negative to positive. That's the other change. So this is a local min. The function f has a local min at x equals -1. So I'll write that down on my little scratch work. I found a local min, and those are the only mins and maxes that this function has. All right, second derivative. Make sure you run this line, so the second derivative is in there. And make sure you run this line to get the solutions in there. Actually, you don't have to run that line. If you're able to copy and paste here, remember we want to change these to decimal. If you're able to copy and paste this, great. Oh, I got that one. And there's actually 3 answers here. And notice there's our -1. Now, if f prime of -1 does not exist, surely f double prime of -1 doesn't either. You can see that in the formula. If you put -1 here in the denominator, you get division by 0. So again, same problem here. But it's not a fatal problem. In fact, we might even write myself a little note here. F double prime does not exist at x equals -1. I can see that from the formula. And so this is extraneous. And I need the other solution here. Let's see if I can copy and paste. Maybe I'll get lucky. Oh, I did. Okay, so we get 2 places where the second derivative is 0 or does not exist. And, well, 2 places where it's 0 and 1 place where it does not exist. -2.48 and -0.85. It's 0. And then at -1, it does not exist. Those are the 3 potential inflection points of this function. So maybe I should remind you of the other way. If copying and pasting is acting up for you, like in my first video, you saw how it kind of acts up for me sometimes. I don't know. There, I kind of forces it to act up. Okay, whoa, craziness. If that happens, let me just remind you quickly of the alternative method. Give this a name. I call it name just for solutions, but you can name it whatever you want. It doesn't matter. I type the name here so that the answer actually prints out. And then we access items in the list again by S bracket 0, S bracket 1, and so on. And I want the right-hand side of that. So S bracket 0 and S bracket 1 are equations. This equation, x equals blah, 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 x equals blah, blah, blah. And we want the right-hand side of that equation. That's the RHS. Okay, so if you can't copy and paste, here's the long way. Of course, we don't need to convert -1 to decimal. That one's okay. All right, so let's see if the sign actually changes. I'm going to start with a -2.48. I'm going to take the second derivative. I'm going to choose something to the left of that, -2.48. I'm going to choose something to the right of that. How about this? Did the sign of the second derivative change? Yes. That means the original function f changed from concave up, changed to concave down. So we have an inflection point. F has an inflection point, oops, at x is approximately -2.48. Okay, here's the next one, -0.85. Now be especially careful with this one because to the left of -0.85 is -1, very close by. So make sure you don't pass, not -9, I mean -0.9. I'm going to choose something between -0.85 and -1. All right, I'll just, there, I forgot the decimal point again. Did the sign change? Yes, so the function changed concavity, so the original function f has an inflection point. Let's abbreviate. At x equals negative 0.85. And the last place is negative 1. So something to the left of negative 1, something to the right of negative 1. Again, be careful about this. You don't want to go too far to the right and pass the other one, the negative 0.85. That's close by to negative 1. Here, there is no sign change. So there is no inflection point at negative 1. Okay, we're not entirely surprised by that because that was the local minimum. But no inflection point at x equals negative 1. It's concave down on both sides, and that's going to be relevant when we see the picture. All right, here's the x-intercept. I'll go ahead and write that down. F is 0 when x equals negative 1. Our old friend negative 1 again. And then the y-intercept is 1. Okay, in behavior, so again, domain is all real numbers, so we're going to take limit of this function as x approaches infinity. And remember, you can either type out infinity or you can put two small o's. And x approaches minus infinity. Those are the ends of the domain. All right, so as x approaches infinity, the function also approaches infinity. So no horizontal asymptote at that side, but as x goes to negative infinity, the function approaches 0. That means we have, f has, a horizontal asymptote at x equals 0. Not x equals 0, sorry, y equals 0. That's the x-axis. Now notice, I'm going to write myself a note, that's on the negative side only. The horizontal asymptote's only on the negative infinity side, not on the positive infinity side. So we'll look on our picture for that as well. Okay, so informed graph. I'm going to plot the function f, my x min and x max. I'm going to look back on my list of important x values that I made, and I see that the smallest one on this list is the inflection point at negative 2.48. Now we saw last time in part 1 that inflection points should not be put on the end of the window. So if I put negative 3 here, that means the inflection point would be really close, and I wouldn't be able to see that. So let's go out a little further. Let's try 10. We can always adjust that later. And the biggest x value I have of all of these things is negative 1. Sorry, not negative 1, negative 0.85. Everything's negative. So maybe we'll just stop at 0. We'll see. We can always adjust that. Now, we can let the computer choose the y min, y max for us, but forgot my comma. Just like I said last time, in order to have kind of a procedure that always works in case it cannot be trusted, I'm going to go ahead and find some y values. The y values that go with my important points from up above. And so there's negative 1, there's minus 5/3, and not 5.3. You know what? I bet if I put 5/3 there, it's going to give me an exact value, and I don't want that. So let's go ahead and convert that to decimal. And here's my inflection points. Minus 0.85. Okay. So, and then of course there's negative 1, which we already have. So I guess that's all we really need. And you can see that these y values are very small. So if you try to just plot this on the default window, you wouldn't see a whole lot because it would happen in a very small range. Now the y-intercept was 1. So that's bigger than all of these. Let's go ahead and go up to 1. If we want to see the y-intercept, we'll have to go all the way up to y equals 1. The minimum y, notice that all of these are positive, so we'll go ahead and start at 0. So let's see what that looks like. And this is not too bad of a graph here. It looks like 10 was, or negative 10 on my x was farther than it needed to be. You know, maybe I would have been okay just at 5. Let's see, play around a bit. Okay, I see concave up here, I see concave down here, I see concave up here. All right, so I see a local min, I see a local max. This inflection point at negative 0.85, which is right around in here somewhere, not easy to see. This is concave up definitely. Hard to see the concave down there. You can kind of see maybe a little bit the bend to make this sharp point. But that's part of the reason why we did the calculus, so that we know that there is an inflection point there, so that concavity changes here, even though it's not obvious from our picture. So let me go ahead and add in the important points. So a list of points, remember, square brackets. So my first point, let's put in the local minimum. That's at -1, well, let's go up so I can see my values. -1, 0. The intercept there is my local minimum. And then the -5/3. And f of that is roughly 0.14. And then we have the -2.48. And the y value with that one is 0.11. And then we have the -0.85. And the y value with that is 0.12. Okay, this takes care of our x-intercept here. And the last thing is the y-intercept, 0, 1. And bracket, and that list of points. And I like to change the color. You don't have to change the color if you don't want to, or you can use a different color. And I like to change the size. Forget what size we used last time. Try that. Okay, so we got an inflection point, local max, local min, and intercept. Inflection point, and this is the y-intercept. Now, this may be a little misleading the way I have this, because it almost looks like the function just stops there, which it does not. It keeps going. It's almost like, let's go up a little higher. Go up too high, then we'll kind of obscure what's down here. This thing just keeps on going up forever, so we don't want to lose sight of that. Maybe I can not go up quite all the way to 2. Okay, I can see that this is going up, up, up forever. The function doesn't stop there at that dot. That dot's just there as a marker of the intercept. Okay, so there's a decent picture of this graph. So now I want to do the absolute max. You know what, I really should have put these little comments in advance so you wouldn't have to type them out. Didn't think of it until right now. Isn't that how it always goes? So, increasing, decreasing, concave up, concave down. All right, so first off, absolute max, none. And please do write none, or maybe make better English than say no absolute max, but whatever, however you want to write that. Remember, this thing just keeps going up forever. That limit as x approaches infinity was infinity. So up, up, up it goes, no top. Now the absolute minimum, right here. This local minimum is the absolute minimum. Remember, this thing is approaching the x-axis. It never crosses, never touches. So absolute minimum is 0. That occurs when x equals -1. All right. At the beginning, why did that just jump down there? My thing, here, let me save it. This thing is increasing at the beginning until it reaches this peak. So increasing, starting at the left side, minus infinity, until it hits the peak. That peak is at -5/3. After the peak, and of course you can put the decimal if you want to. I don't need the fraction, but whichever you like. After the peak, it's going down, decreasing until it hits the minimum at -1. And then it is going up again. Oops. And after that, it's increasing forever. It never turns around again, so increasing forever off to infinity. Okay? Concave up and down. So at the beginning, it's concave up. And so that's from minus infinity until it hits the first inflection point right here, -2.48. And then it changes to concave down, -2.48. Okay, it's concave down until it hits -1. Now remember, -1 is not an inflection point, so it does not change concavity. It's concave down on the other side as well until it hits the next, decimal point, until it hits the next inflection point, -1.85. Now you may be wondering, well, could I glue these two together? No, because of this sharp corner, the derivative doesn't exist there. This is a discontinuity in the derivative, and that allows us not to glue these together. But that's okay. We'll just keep them separate. And then after this, after the -0.85, it's concave up again from there on. So -0.85 on to infinity, it is concave up. Let me reiterate, like I did in the part 1 video, that in the increasing decreasing, these are the local mins and maxes. That's the answers that come here. Of course, if there were domain issues, those could show up too. And these inflection points do not show up here. Now there's some overlap. This -1 happens to show up in where the second derivative doesn't exist and the first derivative doesn't exist, so there's some overlap there. But in general, these inflection points are not showing up here, and the mins and maxes are not showing up down here usually. So try to keep those separate in your mind. We could put square brackets on these endpoints, but we don't need to worry about that. Just go ahead and leave them as parentheses. And again, these are x numbers. There's no y values here, except here in the absolute max and min, there's a y value. Y value is 0. But down here, these are all intervals of x values. So let's keep them that way. Let me go down here and just see if there's anything I want to say about question 2's. Notice the hint here that one graph is not going to show all the important features. We're going to see that this guy, okay, there's division, you're going to have some domain issues. You're going to have to figure out what leads to division by 0. And so figure out when this denominator is equal to 0. And you should check and see if it's a vertical asymptote or a hole, okay, by using limits. There should be some examples of that in the notes. And so when you get down to step 10, you'll have to have one big kind of overall graph so you can see all there'll be 2 vertical asymptotes and the end behavior. But on that big overall picture, you're not going to be able to see all the mins or maxes, especially the right side of the graph. So when you get down there on the right side of the graph of this guy, if you have your points plotted, you'll see there'll be a minimum and an inflection point that are not easy to see on the overall graph. I would recommend doing a close-up of the right-hand side of this graph of G to see that better. But if you have any trouble with that, feel free to ask me questions.